This brings us to Chapter 2. This is all about the molecules of life, or what I like to call it is the Greeks had philosophy and knives. Learning objectives. Oh my goodness, this is a lot, isn't it? 25 different learning objectives for one chapter. This is the most, and we're going to break it down because, as you may have been told before, if you were ever asked, how do you eat an elephant? Maybe you've heard the answer already, but the answer is one bite at a time. So we're just going to take this one and a few smaller size bites. In Biology 1020, the majors version of this course, this covers 4 different chapters. So I'm going to break it down kind of similarly to how we do that in the science majors class. So for learning objectives part 1, here they are. This is what you should know by the end of this video. Hopefully I will explain it to you very well. We're going to look at the particles found in an atom, figure out what atomic number, atomic mass, charge mean, how we know about protons, neutrons, electrons, looking at the charge of atoms based on numbers of electrons and numbers of protons. If I give you the mass number and the atomic number, you should be able to figure out how many protons and how many neutrons are in an atom. We're going to figure out what an isotope is, what makes an isotope radioactive, and then we're going to talk a little bit about chemical bonding. What happens when we put all of these atoms together to make molecules. Okay, so if you ever want the universe boiled down into just 2 things, we can say that the universe is comprised of matter and energy. We'll talk more about energy later, but for now, we're just going to talk about matter. What is matter? Matter is stuff. Matter is pretty much anything that takes up space and has mass that we can measure. Typically, it exists in one of 3 forms down here where we live on Earth, solid, liquid, or gas. But we've discovered there's a 4th phase of matter called plasma. You might find that in your TV. It's different from the plasma that you have in your blood, very different. It is similar to the plasma you might have in your plasma screen TV, but it's not really something that plays a big role in the lives of living organisms. So we'll just concern ourselves with solids, liquids, and gases. Energy is interaction between matter. There's stuff, and the stuff does things. So the matter is the stuff, and the energy is the doing things. So when you move, when you heat something, when chemical bonds are formed or broken, that's all energy that is involved in making that happen. So anyway, back in ancient Greece, the ancient Greeks were known for a couple of things. One was their philosophy, which included their science. They brought science a long way. They didn't have the scientific method, but they were very smart people on the whole. The other thing they're famous for was they did a lot of fighting. They fought a lot of wars, and they had swords and knives and other things. And so what happens when you combine these 2 things together? Well, the Greeks figured that you could take just about any piece of matter, any piece of stuff, and cut it. Cut it in half. You can cut that thing in half again and again and cut it in half again. You can just keep cutting. And they wondered, can you do this forever? Can you cut forever? And they came up with this idea that eventually you're going to have to stop cutting. Even if you made the finest knife or sword or pair of scissors, eventually you're going to get to a scale at which you can't cut anymore. So they came up with the idea of the atom. And up here at the top you can see the roots in Greek. Atomon, which means uncuttable. So they just kind of figured out that atoms exist just by using logic. So we now define an atom, chemists define an atom as the smallest unit of matter that retains its chemical properties. So you probably know that you can split atoms, but when we split atoms, they behave very differently than they do when normal chemical processes are occurring. Okay. The Greeks also figured that of all of the things in the universe, uh, there were just a certain number of substances that you cannot break down by chemical means. So it may not be an uncuttable thing, but there are certain types of stuff out there, substances, that are pure and cannot be turned into anything else. And the Greek idea was that there were only four of these elements: earth, air, water, and fire. But in the age of the scientific method, we now know that there are 90 or so naturally occurring elements or substances that cannot be broken down by chemical means. Okay, and typically they're represented in this table called the periodic table of the elements. And you can see there's a lot more than 90 of them on here. There are currently 118 on this particular periodic table, but a lot of these elements are actually artificial. They have been made by physicists and chemists using some very fancy, expensive machines, applying the scientific method very cleverly in order to create new types of atoms that don't occur in nature. So you can see there's a lot of letters, a lot of numbers here, and we're going to break it down. This is what chemists work with on a daily basis. Okay, so let's talk about the letters first. All elements have a symbol which consists of one or two letters. So typically the first letter is going to be capitalized, and if there's a second letter, it's going to be lowercase. So here are some examples. Gold is capital A, lowercase u. Boron is just B. Uranium is just U. Radon, which is a radioactive gas, is capital R, lowercase n. So, you probably figured out why I've used these examples, because you know what that spells? A-U-B-U-R-N. Okay, so War Eagle. As it turns out, Auburn, as far as I know, is the only university in the SEC whose name can be spelled out with elemental symbols. So congratulations to us. No real scientific significance to that other than, nope, I got nothing. But there are a lot of other numbers on here which we need to explore and explain. So let's get to that. So here we are back at the periodic table of elements. You can see, just like I told you, every element has typically a two-letter symbol. You can see some of these really strange ones out here where they've only been able to synthesize just a handful of atoms. All have these weird three-letter symbols, and their names are basically just the Latin for whatever the atomic number is. And they've just been able to make just one or two or a handful of atoms of these elements, and they only exist for fractions of a second. So very weird things, as opposed to the atoms that make up most of the universe, that they're pretty much here to stay. So only a few of these elements can be found within our bodies. And these elements are pretty consistent across all living things. So when we talk about universal things, certainly the top four and the next 7 are pretty much universal across all living things, from bacteria and archaea to the mushrooms on your pizza, dogs, cats, mosquitoes. All have these same 7 most abundant elements. And 4 of them make up the vast majority of your body's mass. And I would consider them to be very important, which is my code word for, yeah, you should expect to see that on an exam. Carbon, hydrogen, oxygen, and nitrogen, far and away the absolute pillars of life as far as building blocks go by weight. The next 7, maybe not memorize these, but it's good to know that what they are: calcium, phosphorus, potassium, sulfur, sodium, chlorine, and magnesium. And then there are a number of elements that we call trace elements because they make up less than a percent of a percent, 100th of a percent of your body mass. Now, that said, just because they're not abundant doesn't mean they're not important, right? So take, for example, iron here, which is Fe, because there's a Latin word for iron. If there's a Latin word for that element, typically they have a symbol that doesn't necessarily make sense to English speakers, but iron is ferrum, so its symbol is Fe. But the bigger point about iron is that you need iron in your body. It's a component of the hemoglobin that's in your blood that takes the oxygen from your lungs into your bloodstream and nourishes your body so that your body can produce enough energy to stay alive. If you have not enough iron, that typically leads to a condition called anemia. And if you have too much iron, you can be poisoned. So these smaller, less abundant elements have to be managed very carefully by the body. You don't, because a little bit too much or a little bit too little can have a dramatic consequence on your physiology, how your body functions. So we look at this and we can kind of back map this onto the periodic table, and I made it black and white just to make these things stand out. So the most abundant elements are the ones that are shown in red. So carbon, hydrogen, nitrogen, and oxygen are the ones that make up the 96 odd percent. The 3.7% you can see with the orange outline, and then the trace elements you can see in blue. So kind of an interesting pattern to note here that almost all of your body is made up by some of the lightest elements in the periodic table. And everything that makes up your body, by and large, is found in the top half of the periodic table. And this has something to do with just the abundance of these these elements in the universe and on Earth. It also has a lot to do with how atoms behave with each other, if they form bonds, if they're have an affinity for electrons or not. But we'll get into that. That's coming up. Okay, so speaking of elements' properties, what makes atoms different from each other? The structure of the atoms is going to determine what the properties of that element is. So hydrogen, for example, is a gas. Gold is a metal. Carbon is typically just a solid like coal, or diamonds are pure forms of carbon. And the reason that those those atoms act the way they do has to do with what's going on at the subatomic level. What makes up the atom. So the nucleus is the central part of the atom, and in the nucleus we have 2 different kinds of subatomic particles. We've got protons, which are a nuclear particle that has a positive charge, and neutrons, which are nuclear particles that have no charge. And the mass of a proton is very, very close to the mass of a neutron. So if you have 1 proton and 1 neutron in the nucleus, each of those weighs a unit called a Dalton, which is just a unit that's easy to use to apply to protons and neutrons, named after a British chemist named John Dalton. But it's the same thing as what we call an atomic mass unit, or an AMU. And we have a way to convert these into things we can actually measure, grams and pounds and ounces and stuff like that. But for now, we'll just call them Daltons and AMUs. Doesn't really matter. But they weigh the same, okay?